how to calculate measure the time complexity of a recursive program. So what is meant by recursive program? In common sense, recursive means we will do the same steps of things again and again until one condition satisfies. Okay, so we will perform the same steps, again and again until a predefined condition met. So that is called recursive, right? That is called recursive. So in the same way, in programming languages also, while we are doing programming languages, for example, when you want to do a merge sort, or even you want to do a draw fractals, so in many places we will use recursive programming basically, because we are required to do the same steps of same instructions we need to execute again and again until a condition, predefined condition, satisfied. That is what recursive. So recursive programming we will try to understand by using some sample examples basically. First we will take one for loop we will try to understand by using some sample function. So a function or a routine or a method will contain some set of lines, some set of instructions. Those set of instructions will execute while execution at runtime. So for example, I have one function, okay, void means there is no return type for this my function, okay, function. It is expecting one parameter that is called an integer value, and it is expecting an integer value, and this is my function. So what exactly it is doing? We have a one predefined condition. If n is greater than 0, if my parameter n is greater than 0, then perform below operations like print or print something executed. Okay, and these two statements are normal statements, right? But now what we will do is we will call the same function with n minus 1. So this if condition is and here. So this is my piece of code. Now see, if you clearly observe what exactly happening, we are passing n value as an input parameter and it is an integer, and we have a one predefined condition. My condition is if n is greater than 0, then perform these two, execute these two instructions, right? So my first instruction is print some statement, okay, print something, print some string value, and after that what exactly I am doing? We are calling the same function. If you observe, this function name and this function is same. We are calling the same function, but by changing the parameter value, instead of n, we are decreasing. It is decreasing one value. So this kind of instructions we require to write in based on our business logic, or based on our programming language, or based on our requirement. We may end up like this. This what exactly we will call it as? It is a recursive program, right? Because what exactly happening? This function itself it is calling until this condition satisfies, right? this is one of the recursive programming. So now the question is, in previous classes we learned how to calculate the complexity of one for loop and while loop, right? So in the same way, what will be my time complexity of this program? That is what our question. That is what we are going to understand. So now we know this print statement is a constant. It will take a constant amount of time. We already know it. So it will take constant amount of time, 1 unit of time. This function, what exactly it is doing? It is calling this function itself how many times? N minus 1 times. So the time required to complete this statement is required this much amount of time, t of n minus 1, right? So now the total complexity of my function, time complexity of time required to complete this program is 1 plus t of n minus 1. So this we will call it as recurrence relation for this program. So if you observe, this statement is constant time, so it will be 1, whereas this statement, this is calling itself how many times? N minus 1 times. So we mention this as this function, this statement requires t of n minus 1 time. So the total time required to complete this program is t of n equals to 1 plus t of n minus 1, whereas my n value is greater than 0. So for example, if my n is 0, that means what will happen? These two things won't execute itself. If my n is 0, these two instructions won't execute. So this recurrence relation won't be applicable. So this is the amount of time required to complete this program where my n is greater than 0, right? Everyone understand, right? Now this is the amount of time to require to complete this program. Now we will try to see what is the complexity in a function. Right? We learned this so much in our earlier classes. Constant n, root n, log n, n square, n cube, n power n, right? Exponential, polynomial time, everything. So we will try to understand how can we find the complexity of this program by using a recursive tree. Okay, so what we will do is we will execute this program via a basic tree structure. So what exactly we will do is, first, for example, let's imagine this first time I am calling with n. Let's imagine my parameter is n for this function. So first time I called this function. Okay, what will happen if my n is greater than 0? Let's imagine my n is greater than 0. Then what will happen? This statement will execute. How much time this requires? 1 time it will execute, and this requires constant time. So 1 time I will print this statement. After that, what exactly we are doing? Again I am calling this function itself, but by a decreasing value, t of n minus 1, right? So first time I called n, I passed n, then it will print the statement. Again the same function will call with n minus 1. So again what will happen? Again t n minus 1, again this statement will print 1 time, and this will become t of n minus 2, right? So till how many times it need to execute like this? This, if you see, this is a tree of this execution pattern basically, right? So how many times I need to represent like this until my n becomes 0, right? So when my n becomes 0, then I will stop my execution. So I need to keep on going like this until t of 1 one time, next t of 0 will come. I will write down here. So after tn minus 2, tn minus 3, go on, t of 2. So if I pass t of 2 this, what will happen? 2 is greater than 0 and I will print one more time, and again I am calling t of 2 minus 1, right? T of 1. So now 1 is passing, 1 is greater than 0, I will print one more time, and I am trying to call t of 0. So when my n becomes 0, n is greater than 0, wrong, false, right? So my execution will stop here. So this is the recursion tree for this given program, recursive program. So if you say how many times we are executing this, basically if you pass instead of n, if you pass any example like 3 or 2 or 5, how many times we need to repeat this, perform this thing? Basically n times we need to do it. So my complexity of this program is order of n. We will see with one example with 3. Okay. So let's imagine my n is 3. Okay, first I will call this function t of 3. Then what will happen? Print statement will print one time, constant time. Then 3 minus 1, it will become 2. Then what? Again t of 2, 2 is greater than 0. Then one time I will print, and after that t of 1, because 2 minus 1 equals to 1. Again I will call this function. 1 is greater than 0, I will print one time, and 1 minus 1, t of 0. So when I am trying to pass 0 value here, my condition, predefined condition will met here, satisfy, and it will stop the execution, right? So this, how many times we done this? n times, basically n times. So the complexity of this recurrence or recursive program, complexity is order of n. So this is my recurrence relation. This is my recurrence relation. So how we calculated? Using recurrence tree. There are other ways also, substitute mechanism, and finally we will discuss about Master Theorem. There is no need to draw or represent in this format. By using simple theorem, we can, by seeing this function itself, by applying that Master Theorem, we can easily come to this conclusion. We will discuss at end of the class here. Okay. So now I hope everyone understood, right? Now what we will do is we will change a little bit of this our function, and we will try to understand one more time. So I am keeping the same function, but we will try to change little bit here. If you observe, we are calling this function by using n minus 1. We are decreasing the input parameter. For example, what will happen if I increase this instead of minus, if I place plus, what will happen? Anyone? What will happen? Just think of it. That will be endless, basically, because your n never will be, this condition won't satisfy if we pass instead of minus, if we pass plus addition. So that's the reason whatever we are going to discuss today, whatever I am going to explain, those things will be minus, decreasing, or let's divide, or square root. We won't do addition or multiplication, because if we do place addition plus symbol or star symbol, multiplication symbol here, what will happen? This condition we need to change in some different way. We need to change some different way. Otherwise, this won't end, because n will increase every time n will be greater than 0, and this won't stop. So it will be endless, forever loop. So now I hope everyone understood, right? Because this is, if you understood properly, it will be better, so that I can go for other example. Otherwise, we will try to spend some time on this only, right? Okay. So now what we will do is, we will just tweak this program by adding some for loop. We will make ourselves so little bit complex to understand properly our recursive program. So here what exactly we done in previous scenario, we simply printed one statement. Now what we will do is, in between this, we will print this statement in a for loop. For I equals to 0, I is lesser than something, n I plus plus. Okay. So now we made ourselves little bit complex to understand our recursive programming complexity, how to calculate the complexity properly. So it's same, but the small difference is, if you see this print statement now, previously it was a constant time, but now because we added one for loop, and we know what will be the amount of time, what is the complexity of this for loop. We learned this in previous classes. So this statement complete, this now print exe, whatever it is, print statement will take how much time? N time, n amount of time, right? Previously it was 1, now because of our for loop, it requires n. Now as usual, this is same. This will be t of n minus 1, because there is no change here. So now what will be my recurrence relation for this program? T of n equals to, instead of 1 previously, now here n plus t of n minus 1. So if you observe previous scenario and now only the change is, previously here 1, now it is n. So this for n is greater than 0. Right? Same condition will apply. If my n is 0, then these statements, this for loop or this recursive function won't call. If my n is greater than 0, then only these two statements, now for loop and recurrence, same function, will call multiple times. Okay. So now this is my recurrence relation for this program. So now we will try to calculate the complexity of this program, piece of code, by using same method, by using same recursive tree. So let's imagine I am passing n to this function. What will happen? In previous case, when there is no for loop, I simply mentioned as 1. But now I can't mention, because there is one for loop, and this requires n amount of time, because my n is n. So n times, if you see, n times we will print this statement, right? N times we will print this statement. Previously it was 1, but now n times we will print this statement. And what else we are doing? Again I am calling n minus 1 times again. So what will happen again? So here how many times I will print? Because my n will be n minus 1, so n minus 1 times I will print, and again I will call t of n minus 2, right? So this is same as our previous case. So in this case also, how many times we need to repeat? Until this condition satisfies. So when this condition will satisfy, when my n becomes 0, when my input parameter becomes 0. So I need to repeat this pattern, repeat this tree. For example, t of 2. That means how many times I will print? 2 minus 1 times. And here I will call t of 1. T of 1 0 times. So here t of 0 will come, my condition will stop. Right? So now what exactly happened? Exactly how many times we are executing? Let's add up these numbers. We will get n, this is n, plus n minus 1 plus n minus 2. If for example, for our understanding, instead of t of 2, if I say times n minus 2 times and n minus 3, right? N minus 3. So this will go on t of 2, 2 minus 1 times, right? So 1 time, and t of 0, sorry, t of 1. T of 1 means 0 times, and t of 0, right? Right? So n minus 1, n minus 2, plus so on 2 plus 1 plus 0, right? This is what the final value. So now what is this actually? This is, we are simply adding. So this will become n into n minus 1 by 2, right? Sorry, n into n plus 1 by 2, right? So this will be n into n plus 1 by 2. So what is the complexity of this? Order of n square, right? So order of n square. So this is how, now because we added one for loop, our complexity of this program got increased, order of n square, right? Previously in our case it is always 1, right? So it becomes n times, but in this case, if you observe n minus 1 plus n minus 2 plus n minus 3 plus go on to 1 0. So this is adding n into n plus 1 by 2. So the complexity of this program is order of n square. So by using recursive tree, we calculated the complexity of this program, and we identified what is the recurrence relation for this program. Recurrence relation for this program is t of n equals to n plus t of n plus t of n minus 1, right? Where n is greater than 0, right? Now what we will do is, we will try to add complex this same function by adding some other few lines. We will try to understand some more. So now we will see another example. We will keep the same function. But we will try to change the for loop here. So previously, what is the for loop? For I equals to 0, I is lesser than n, and I plus plus. Instead of I plus plus, what we will do is I equals to I multiplied by 2. So okay, here. Okay, so I equals to 0, I is lesser than, I equals to I multiplied by 2. The remaining thing is same for our program. This is our business requirement. Just imagine, instead of printing n times, I want to print how many times? We already learned this. How much time it requires when I equals to I multiplied by 2. This statement requires how much time? Log n times, right? This is all. This for loop you already learned how to calculate the complexity of this program. So because I know and you know what is the complexity of this for loop, that is log n times. So again we know this is same as t of n minus 1, right? This is because there is no change. Only change is this, because of this I equals to I by 2. Previously, when my I is I plus plus, it requires n, right? Now it requires log n. Complexity of this statement for loop and statement requires now log n times. So what will be my recurrence relation for this program? Is same as t of n equals to, instead of 1 n, now we got log n, right? Log n plus t of n minus 1, whereas n is greater than 0, right? This is my recurrence relation. Up to this, everyone clear, right? There is no complexity, because we know how to calculate the complexity of this for loop. We discussed this already in our earlier classes, right? In n, because we know this requires log n and log n amount of time, and this we know already t of n minus 1. So this is my recurrence relation. Now, what is the complexity of this program? We will try to find by using our recurrence tree method. Same methodology we can apply. So initially, what is my t of n? Let's imagine my n is greater than 0. Then what happens? This, what exactly I am doing? Log n times I am doing this. After that, what I am doing? I am calling myself again. and I am now this time log n minus 1 times, right? Because now my n is n minus 1. So I simply replace n here, n minus 1 here, and what I will do? T of n minus 2. And this will happen times log n minus 2 and t of n minus 3, right? This is same pattern, but the thing here, the previous case and here, what is the change? Only we are adding log here. Remaining things are all same. If you observe, n minus 1, n minus 2, n minus 3, go on up to what? T of 2, okay, log how much then? 2, T of 1, log 1, T of 0, right? So when my input becomes 0, I will stop my execution. This is same as our previous example where I equals to I plus plus. Now because we are executing this inner statement in different way by using different logic. Now we require to add log here. For example, if we have something else or some other logic here, then we need to add that value here basically. So now we can apply the same thing how we done previously, log n plus log n minus 1 plus log n minus 2 plus so on log 2 plus log 1, right? This is same as our previous scenario, right? So here log is common in all phrases. Log is common. So what we will do is we will separate it out. Log. If you see n, n minus 1, n minus 2, this is what it will become n factorial basically. N factorial. So if you transform this statement, it will become log n factorial. Now, how many of you remember for n factorial there is no theta notation, right? There is no theta notation, right? So what will be my complex stuff? N factorial. What is my complex stuff? N factorial. N power n, right? N power n. So it will become log n power n. So this can be translated as n log n, right? This is logarithm by using logarithm application. So we will apply logarithms here, and this n will come here. So it becomes n log n. So my complexity of this program is n log n because I changed this for loop and we ended up here, right? So this is the way we can identify, we can calculate by using recursive tree, and this is my recurrence relation. Okay, so this is my complexity of this recursive program. Now okay, now what we will do is we will try to tweak this thing. Instead of this for loop, we will try to tweak this thing, this statement. Let's see. So now what we will do is we will change a little bit of this program. So we will remove this print some statement here, exc, and so we are calling ourselves by using this statement, and what we will do is we will call another time. Not only one time, we will call another time by using n minus 1. So what exactly we are doing here? If my n is greater than 0, print this statement, and I am calling this myself, and once again I am calling this myself. So here we are calling 2 times instead of 1 time. So what will be my recurrence relation? So as usual, this print statement is required constant amount of time. This is required t of n minus 1 and this is required t of n minus 1, right? So what will be my recurrence relation for this program? T of n equals to, because we are two times we are calling that, because we are calling two times, right? So 2t of n minus 1 plus 1, or we can represent as 1 plus 2t of n minus 1. So this is my recurrence relation. Now because here 2 came here, why? Because we are calling two times. For example, if I am calling 3 times, it will become 3. If I am calling 100 times, it will become 100, right? That's simple. So there is nothing to worry about it, but this is what my recurrence relation when my n is greater than 0. Right? Now we will try to calculate the complexity of this program by using our recursive tree methodology. So I need some more space here because we are calling two times, right? So my branches of tree will expand basically. So for example, my t of n is greater than 1, 0, then what exactly I am doing? I printed one time, okay, this is constant time, then I am calling this t of n minus 1 and at the same time I am calling second time t of n minus 1. So instead of one branch, I got now 3 branches basically. So again what it will happen? Again it will print one time and it will call t of n minus 2 and t of n minus 2. So in the same way it will have 3 branches. It will print one time and t of n minus 2, t of n minus 2. If you will see what will happen, again this statement will print one more time and it will become t n minus 3, t n minus 3. For this also same thing, for this also same thing, for this also same thing. So this thing up to what we need to do? Up to this, until this condition satisfied, right? So if you observe how many times I need to repeat this branches, basically this pattern. First time one time, second time 2 times, third time it will become 2 power 0, 2 power 1, 2 power 2, 2 power 3. Like this it will go on. If you draw your own, you can observe. If you have some more space or you can write it down on white paper, you can find out the pattern. You will clearly observe in this fashion. 2 power 3, 2 power 4, 2 power 5, like that. So we will do this up to 2 power k times. So when I reach 2 power k, that means I am satisfying this condition for all the branches, right? That is what this 2 power k means. So this increment I need to do up to 2 power k so that this condition will met, right? So I will erase this branch basically. I need some space. So this is what we left with. So we know 2 power 0 plus 2 power 1 plus 2 power 2 plus so on 2 power k. So this thing we can represent as 2 power k plus 1 minus 1. You can do it yourselves also. For example, So 2 power 0 is means what? 1, right? Basically. So 1 plus 2 plus 2 power 2 plus 2 power 3 equals to 2 power 4 minus 1. Okay. So if this is my 3 is my k, what will be the value of this one? 15. So 15 equals to 15, right? If you calculate it, we will get 15 equals to 15. So we can represent in this format, 2 power k plus 1 minus 1. So assume now we will try to remove this k. We will try to replace k with n value. So basically n minus k equals to 0, right? So now assume n minus k equals to 0. N minus k equals to 0. Then what will happen? N equals to k, right? So instead of k, I can call it as 2 power n plus 1 minus 1, right? 2 power n plus 1 minus 1. So what will be my complexity? Order of 2 power n. Okay. So this is how we calculated by using recursive tree method. So as I said earlier, there is no need to do this much, no need to spend this much amount of time on drawing this recursive tree, or we have other substitution methodology also. So there is no need to spend that much time. By seeing this program itself, we can easily identify the complexity of this program for given recursive when there is a recursive pattern, recurrence pattern, by using Master Theorem basically. Master Theorem will be separate for subtraction when n minus 1 as well as divide. That means n by something, n by some value, n by k or something. So if we are decreasing, in decreasing order we are going, then we need to apply the Master Theorem of decreasing. When we are doing division, then we need to apply other equations. Basically, we need to use that Master Theorem definitions or those patterns basically. So now I will erase this one. So this is Master Theorem for division basically. This is Master Theorem for division. This is a definition of Master Theorem. So you can go through yourself. It's very easy. So this is T of n equals to T of n, for example, T of n equals to in previous case we seen that T of n minus 1 plus 1. Here A is 1, because if you take this example, because there is no value 1 here, A will be 1 here, n minus 1, B will be 1, okay, B will be 1, plus 1 is my f of n, that is function. Here we can call, instead of n 1, we can represent as log n, anything we can replace here. So this is what we have, three conditions. If for example my A value is here, in this case 1, in this case 2, in this case 5, right? So how to come to the conclusion, how to calculate the complexity of my recursive program complexity? By using recurrence relation. So whenever you have a recursive program, the first thing what we need to do, we need to identify the recurrence relation for that particular program. We know, right? We already learned that. So first, whenever you see this kind of recursive program, first try to write down the recursive recurrence relation for that application. Then you can apply Master Theorem if you are seeing minus here, so division. Okay, sorry, not division, decreasing order. Okay, so if you see, if you apply this condition on these things, you can figure it out what will be the complexity of this recurrence relation. This, if you see this, each and every recurrence relation represents one recursive program, right? Recursive program. If you see here, we are calling only one time myself. In this case, I am calling myself 2 times. In this case, I am calling myself 5 times. So here A will be 1, but here A is greater than 1. So when A is greater than 1, we need to follow this or this. If A is 1, this or this we can represent. So if in this case my A is 1, so I can represent in this format or in this format, right? So let's imagine what will be the complexity of this program recurrence relation. Because my A equals to 1, then I can apply one of these things. So n multiplied by what is my f of n? 1. So big O of n. My complexity of this program is big O of n. So for this program, for this recurrence relation, in this case my A is 2, so A is greater than 1, 2 is greater than 1. So I need to use one of these things here, right? So this will be the, what will be the my complexity? 2 power n. 2A is 2 power n, because here only 1 is there, right? So there is no need to represent, add here. In this case, A is 5, so 5 power n. For example, here instead of 1, if I have n here, instead of 1, if I have n here, then what will be the complexity of this program? N, because n power k, here n power k is 1 only, right? N power 1, we can represent this as n power 1. So n multiplied by what? 5 power n. So this is what Master Theorem. You can use this Master Theorem to calculate the complexity of a recursive program. So use the first thing we need to understand, whenever you see a recursive program, first we need to write down the recurrence relation, then we need to apply this Master Theorem. These definitions are applicable only for decreasing order, if you observe when there is n minus 1. If here n by some value, then we need to apply other rules we will discuss after this. So now we learned about recursive programming, how to calculate the recursive programming for decreasing order functions. Right? Now we will see same program, but instead of n minus 1, we will call by n by 2. So let me write down the same method, void function int n, everything is same, if you see, and if n is greater than 0, okay, print something, print exe something, then I will call myself function, instead of n minus 1, what we will do is n by 2. So only thing is, this is the thing. So instead of decreasing, we are doing division here. So whenever you see this division, we need to apply Master Theorem of division rules basically. But before applying Master Theorem, learning about Master Theorem of division rules, let's try to find out what is the recurrence relation for this division function basically. Relation for this program, okay, T of n equals to, because we know this will take constant amount of time, 1 plus, now this is, previously when n minus 1, T of n minus 1, now in this case T of n by 2, that's it. So this is my recurrence relation when n is greater than 0. Sorry, n is greater than 0. So, n is greater than 1. I just take this, n is greater than 1. Okay, now we find out the recurrence relation for this program. Now the next question is how to calculate the complexity of this program by using recursive tree. So we will do the same steps what exactly we done for decreasing order. Let's imagine T of n. Then what I am doing, we are printing one time, and after that what I am doing, I am calling myself by n by 2. So what will happen is, when this calls, again I will print one more time, and n by 2, right? So what it will happen, it will print one more time, n by 2. So if you observe, if you do what exactly we were doing, I need to do this thing up to n by 2 power k times. So when I reach this, I will satisfy this condition so that I will stop my execution. So these things, how many times I am doing? K number of times I need to repeat. 2 power 2, 2 power 3, this is 2 power 3, this is 2 power 2, 2 power 1, 2 power 0, 2 power 2, 2 power 3, 2 power 4, 2 power 5, up to 2 power k times I need to repeat. So what exactly this means? This means when I reach here n by 2 power k times, that means my condition satisfied. N by 2 power k equals to 1, right? That is what? When I reach this position telling me you reach this position, that means you are reached to 1, the value of 1. So this can be, we can represent as n equals to 2 power k, right? So cross multiply, n equals to 2 power k. So this we can represent as in logarithm basis, right? Log base to n equals to k, right? So what is my complexity? Complexity is log n. So my complexity of this division is log n. right? Everyone understood, right? Okay. So now we will do the same things, we will use same for loops what exactly we done for our decreasing order function also. So now instead of one simple print statement, we will use for loop. For I equals to 0, I is lesser than n, I plus plus. So we will change the for loop. So what will be the complexity of this program? So we will do the same logic, t of n. T of n, what exactly I am doing here? I am printing n times, right? N times. And after that what I am doing? I am calling myself t of n by 2. After that what will happen? N by 2 will come here, input as an input, n by 2 is greater than 1. And so this will print how many times this time? N by 2 times will print, not n times, because my input value is n by 2, so I need to print n by 2 times. This for loop will work n by 2 times. And what I will do? Again I will call myself n by 2 by 2, right? So it's same thing, but here the execution pattern is changing, right? So this thing we need to do up to 2 power k times, right? N by 2 power k times, right? So as we done in our division, we will try to add up these things, n plus n by 2 plus n by 2 power k, right? We can separate n 1 by 2 plus so on 1 by 2 power k. Okay. So this value will become 1 when we calculate, so we will left with n. So my complexity is big O of n. So my complexity of this program is big O of n when we added for loop here. So in the same way, if I call 2 times, just try from your side how it will be. It's the same thing, but you will get the different complexity of that program. So this is Master Theorem for dividing. So here we have 3 different scenarios. If you can observe, when log BA is greater than k, log BA equals to k, log BA less than k, and when log BA equals to k, then we have 3 other conditions. Based on these values, we need to use one of these mechanisms, formula. Basically, when log BA is less than k, then if P is less than 0, big O order of n power k. Or if P is greater than or equals to 0, then big O of n power k log P n. So this is Master Theorem for dividing. Instead of writing all the recursive tree or using substitution method, you can use these formulas when you find a recursive function with dividing. Okay, so for example, this is our recursive recurrence relation for our program where we are using division. So 16 times we are calling ourselves, and we are using dividing and plus n time. N time means, for example, we have one for loop. Okay, so by using recursive relation, how to calculate the complexity of this program. So if you see, what is my A equals to 16, and what is my B equals to 2. So log BA, what is log, what is my B, 2, what is my A, 16. So what will be my value, 4, right? 2 power 4 equals to 16. So I got 4. Okay, now what is my K value? N power 1. So my K value is 1. So 4 is greater than 1, right? 4 is greater than 1. So this condition met, right? This condition met. So what will be my complexity of this program? But we can apply this formula. So my complexity will be big O of n power log BA. Log BA is what? 4, right? So n power 4. So my complexity of this recurrence relation is big O of n power 4. So instead of writing all recurrence tree, we use applied Master Theorem of division to calculate the complexity of this recurrence relation. Right? Hope everyone understands. So we need to memorize, or we need to have these formulas before apply to find out the complexity of our recurrence relation. This recurrence relation will come from a program, right? We know how to do it. Now we learned about decreasing and division, right? Now we will try to understand square root. When we have a square root in our program, how to find the complexity of that program. For example, same program we can take void function, this function taking integer n value, okay, and because we are doing square root, then if n is greater than 2, then we are saying print something, and I will call myself. Now this time root n, we will use root n instead of n minus 1 or n by 2. Okay, now we need to find the complexity of this program. Before doing that, we need to find the recurrence relation for our program. So t of n equals to, this will take 1 time and this will take root n times, t of root n, right? So 1 plus root n. So this is my t of root n. So this is my recurrence relation. Now by using recurrence tree method, we will try to find out the complexity of this program. So t of n, it will print 1 time. So t of root n, right? T of root n. So I will change this as t of 1 by 2, n power 1 by 2. I can transfer this. So this what will do 1 time, and what it will so what it will happen, 1 by 2 power 3. So again this will repeat up to n power 1 by 2 power k. Okay, up to this times we need to traverse, we need to do this thing, so that this will match with this condition so that our program execution will stop. That means what? N by 2 power k, sorry, n power 2 power k equals to 2. That is what I am saying, right? This is what we are saying. So what this can be represented as n equals to 2 power 2 power k, 2 power 2 power k. So this will be log n. So my complexity of this program is big O of log n. This is the way we need to find out the complexity of square root function. Basically root function, whenever you are using root functions in your program, we will find out this way, or you can use substitution method. I am not telling you, but for easy understanding, this will be, if you understand properly, you can do other things also.